For example 3 on our chapter on transfer functions, we're given a slightly different form of a set of equations of motion. There are actually two first-order equations. The output variables are x and y. We have an input on the second equation of f. And again, since they're the first order, you see, or that's based on the fact that the highest order derivative in each one is 1, the first one having an x dot, the second a y dot. What we want to do is find the transfer function that relates x to f. We want to find the transfer function that relates y to f, as well as the poles of the transfer function. We want to characterize the free response in the system from what we know about the poles of the transfer function. Since we're looking for transfer function, we only care about forced response. And since we're only looking at forced response, that means that when we transform our equations of motion, we can use zero initial conditions. We don't care what they are because that doesn't dictate anything about the transfer function. So if we now take Laplace transform of our equations of motion with zero initial conditions, the first one's going to be a 3s times x minus the transformed y, and that's a 0. I'll call that equation 1. And my second equation, which is coming from the transformed second equation with zero initial conditions, that's an s plus 6 times y of s plus 4 times the transformed x, and that's equal to the transformed input, which I'm going to call capital F. So for our first part here, finding the transfer function between x and f, I'm going to look at equation 1 first. From that, I get the relationship between y and x. Y is equal to 3s times x. If I substitute this into equation 2, I get s plus 6. That's multiplying the y. The y has a 3s in there times the x, and then there is a 4x, like that, equal to f. So therefore, it's a matter then of just solving for the ratio of the output of interest x divided by the transform of the input f of s. So that's going to be equal to 1 divided by 3s squared plus 18s plus 4. This is our denominator of interest. This is d of s, and this, of course, is what we define as our transfer function. But being as we have more than one, we need to distinguish one from the other. So I'm going to call this a gxf because that relates the input f to the output x. Then for the second part on transfer functions, if we want to know y of s, we get from equation 1 that y of s is equal to 3s times x. We got that from equation 1. We substitute in our relationship that we got from x above, so this becomes a 3s divided by 3s squared plus 18s plus 4 times f of s, and that is our transfer function between y and f, as that. So what we have here is a numerator of n, which is 3s. The denominator is no surprise. It's the same one as we had for x. That's one thing we will find between the transfer functions, is that the denominators will be the same. And from what we've seen before, we don't really need to go back now and look at the transformed free response equation, simply because everything that we need to know is dictated by d of s. So let me just write that down. The character of the free response, not the details, but the character of it, is dictated by the poles. In other words, we can get that straight from the transfer function. So d of s for both x and y was 3s squared plus 18s plus 4. We find the roots of that, the poles, by setting d equal to a 0. We have a quadratic equation. So our two poles, p1 and p2, are going to be minus 18 plus or minus 18 squared minus 4 times 3 times 4. Divided by 2 times 3. And our two roots end up being real. One is minus 5.77 and the other is a minus 0.231. Importantly is they are real and negative. That tells us a lot about what we expect on the free response. And we can just write that down. Since we have real, distinct poles with, I should say not with, but that are negative, we don't have to find the response. We can simply say that we have two parts which are both decaying exponentials in time. So keep that in mind as you look at problems with transfer functions. The transfer function is really used primarily for finding force response, but along with that we gain information on the character what the response would be, even just to initial conditions. There's an additional question I could have asked, and maybe in retrospect should have asked on this one, is this. We have two coupled first order equations. What would be the time domain input output equation for, let's say, y of t? You know, we've done this before back in I guess maybe back in chapter 1 when we were still talking about deriving equations of motion. We talked about ways, we worked with ways of taking coupled equations and reducing that down to a single input-out equation depending upon what output that we wanted to have. As we've talked about in the lecture, the Laplace transform approach allows us to easily get that without having to go back and look at each problem individually as far as what method you might use. With all this said, what I'm going to do is go back to an equation here for y of s. Y of s was right here. I'm going to write that down again, but what I'm going to do is pull the denominator of d back over here on the left hand side, and what I will get from that will be 3s squared plus 18s plus 14 y of s, and that was equal to 3s f of s. Okay. So you could, although we didn't actually have that equation, the time domain input-output equation, if we took the Laplace transform of that, if we had it, this is exactly what we would end up with. So we can now go backwards from this and say that the 3s squared times y, that's going to inverse Laplace transform. That's going to give us a 3y double dot. The 18s times y, that's 18y dot. And the 14y, well, that's just 14y of t. The right-hand side, we have an s times f. We do the inverse Laplace of that, and we get df dt. So this would be our equivalent input-output time domain equation for y of t. We could have done an equivalent thing for x. We just would have started with the form for x rather than y. So again, the idea here is that once you've transformed stuff, you can manipulate things around in an algebraic sense and get us back to the time domain equation that we can get from other means, but maybe not quite as easily as this.